And today I'll present something about the least risk profile in indoor space. We heard a lot about 3D acquisition in indoor space and indoor modeling. But I will talk about indoor navigation and then more specifically the algorithms for indoor navigation. So a short kind of problem statement introduction. My focus, as I said, is on indoor navigation, the indoor networks and the algorithms. And when I kind of look and research at the algorithms that are used currently in indoor navigation applications, I only bump on the extra shortest path algorithm. It's the only thing I see basically. And I was like wondering, like, sometimes the shortest path indoor is not really what people would like to use when they navigate in the building. So it's kind of like a disagreement between what people would want to have as a path in a building and what they would get from having the shortest path algorithm, the calculations from the shortest path algorithm. So in the outdoor space, in the outdoor world, there are a couple of cognitive algorithms. I call them cognitive because they're cognitively richer. They are closer to our natural wayfinding. A couple of examples are the simplest paths, the simplest instructions, and the least risk path algorithms. And so it was always strange to me that indoor environments, in my perspective, are actually more difficult to navigate. There is less visibility. It's always like walking a box. You have less orientational clues. You have the multiple floors. So it was always like I need an algorithm when I walk in a building that I don't know that helps me navigate and helps me not get lost in the building. So that's why I'm currently working on extending and adapting the outdoor cognitive algorithms to the indoor world. And in this presentation, I will focus on the least risk path algorithm, but I'm also working on the simplest path algorithm in the hope to have a more cognitive algorithm for indoor space. So the research questions, the start is basically I implemented the original algorithm from outer space in indoor space, and then I wanted to test and analyze on two levels. First, is the least risk path indoor equivalent, are the results equivalent to the situation in outdoor? Because it has this kind of same connotation. Is there a similar difference with the shortest paths or not? And then more into detail about the selected routes that are calculated by the least risk path algorithm. Is the routes that we get, are they actually less riskier? Are they cognitively easier or not? So that are the two analysis levels that we will see later on. So what's the least risk path algorithm all about? It was originally mentioned first time by Krum in 2005, and she described it as the path between 2 points having the least risk of getting lost on your way. So it will select all the edges and nodes where you will have less risk of getting lost compared to other paths in your building. The risk is measured at every intersection, and it is calculated as the cost for taking a wrong decision. So here's an example. If you come from I minus 1, you go into this intersection I, and you want to go to I plus 1, the total risk of the path is the sum of all the lengths of the path lengths, so the green arrows, plus the sum of the risk values at each intersection. And the risk value at this intersection is calculated as the sum of all the length of the wrong choices, being A, B, and C, times 2 because the algorithm assumes that if you're at an intersection and you take a wrong edge, that you will notice it at the next intersection that you went wrong and you go back. Obviously, that's a big assumption, which we probably will address later on when we adapt the algorithm. So times 2, and then divided by the number of possible choices, in this case 4. So it's kind of the average length of a wrong choice that is calculated. The structure of the algorithm is similar to the Dijkstra shortest path algorithm, but the cost calculation is more complex because the risk value takes into account the length of the edges that you don't use, and if you have to recalculate the path, it has to take into account also the other edges. So it's not as easy as it might look in the beginning. I said I implemented the algorithm, and therefore I had a test data set. And that's the Plateau Z building. It's actually the same building where Viaene did this experiments with in the landmines. It's a building of Ghent University. It has like 4 or 5 floors. For this test, I used the ground floor and the first floor, and So the map shows the ground floor, with all the green areas are just offices and conference venues and just normal spatial units. And the brown areas are all the corridors connecting everything. The gray ones are outdoor areas like inner courtyards that connect different indoor areas. And the orange-red ones are the connections with the first floor. And the network, you can see that there's a network on it. I use networks obviously for my algorithm calculations. And in this case, I used a geometric network model that was developed by Lee, GM. I used that because it's kind of the main accepted indoor network up to this point. So maybe later on I will play around a little bit with the network structure. So then I wanted to analyze it, like I said, in two ways. First, the comparison of the entire data set. How alike are the least risk and the shortest paths, and then more in depth to actually see if the routes that are calculated are actually less risky compared to the shortest path programs. So the first general analysis, what we did was we calculated for each node paths to all other nodes in the building. And we did that for the entire building, for the ground floor and the first floor, and also for the least risk path and the shortest path. So in total we had like 400,000 paths calculated. The result of the algorithm gave three values: the length, the total path length, the risk value, and the total risk value, which was a combination of the length and the risk value. In the table you see the differences between the results of the least risk path and the equivalent shortest path. So if you have a path between two nodes, you have the least risk path calculated and the shortest path, and then we took the differences between the values that we got from both. And it shows that the least risk path has an average length increase of 4.5 meters, but the risk value theoretically was decreased by 15.5 meters. So that was kind of the trade-off. You get a longer route, but theoretically you should get less risk of getting lost by taking the route. Then if we compare the results of the indoor and the outdoor least risk path, we see that indoor, the least risk path on average is 4% longer in terms of length, obviously. In outdoor case, it was 9%, so it's kind of comparable. Obviously, the paths in indoor space are a lot shorter, and there are less possibilities because of the network structure. Then we went more into detail for the length increase. We wanted to see if the increase that we saw in length was, if there were certain paths that had bigger increase, how many paths were actually longer, significantly longer than the shortest path. So it's a classification of the paths, and we see that like kind of all these three, 70 to 80% have an equal length, so are completely equal to the shortest path, or are maximum 10% longer in terms of length compared to the shortest path. So it's kind of shows that there's only a limited difference between the shortest path and the least risk path indoor in terms of path length and risk value, which might indicate that basically the least risk path might coincide with the shortest path, and that might mean that the shortest path is already the least risk path, or that the algorithm, the original least risk path algorithm, doesn't really work well in indoor space. Next, we wanted to know if there were differences in the variation, the internal variability in our building, if certain areas perform better or worse in terms of being close to the shortest path route. So these two figures show on the one hand, on the left-hand side is the ground floor and the right-hand side is the first floor. It shows the standard deviation of the length difference. And the red dots show high difference in standard deviation, so that means that the shortest path and the least risk path deviate a lot for all paths starting in each point. The blue ones have a low difference, are more equivalent to each other. So what we can see is that on the first floor, a lot of blue dots occur here, so there's not a lot of difference between our paths or shortest path and our least risk path. If you look at the ground floor, we see more red dots because the network is much denser, so there are more possibilities to deviate. And it's also around staircases. If you get the staircases right here, right there, there are more options to deviate when you go to a first floor and then come back to the ground floor. So we kind of see this first view on the deviations. Then we wanted to see actually how the paths are embedded in space. So we want to have a path correlation, and we did that on two levels in terms of node use and in terms of edge use. So we calculated the path flows, the number of times the path uses a certain edge, and also the Japan similarity coefficient, which is the number of nodes that are equal in path use. So we have some results for, this is for one specific node. So we calculated from starting here in this, obviously you can't really see it because it's covered, from a node on the first floor, all paths to all other nodes in the building. And then we counted all the number of times each edge was passed. And the bigger the line, the more that edge was used in both. This column is for the least risk path algorithm, and the bottom column is for the shortest path. And the first row is for the first floor, and the second row is for the first floor. This is for the floor. So what can we see from this table? If we start with the shortest path, we can see that a lot of paths kind of take this southern, here is the staircase, take the southern located staircase, and then, if you see here is the end of the staircase, deviate to other areas in the building. While in the least risk path, it's more dispersed. Some of them take this staircase, and others take that staircase. You can see it. So these areas in the middle of on the ground floor actually they have different paths if you see the difference between the shortest and the least risk path. Then the second path correlation measure is the ratio of equal nodes by the total number of nodes. The redder the dot is, the more equality there is, the bluer the less equality there is. So again, we see that the source node is here, so everything close to the source node takes the same path in the least risk path and the shortest path. The only thing that is different here, in terms of results, is that here the dots are not as red, and here as well, on the first floor, but on the previous, you couldn't really see any difference between the shortest path and the least risk path, and that was because these edges are not used very much, because there are only so many rooms there. But if we look at the node use, then we can see a difference. So the location of the stairs is of major importance in the section of the paths, and neighboring nodes have similar path structures. Then we wanted to actually examine if the least risk path algorithm actually calculates routes that are less risky to get lost on. So we did that by choosing one example. In our work, we did more examples, but I'll show you one example. So it's kind of a worst case example where the least risk path is 42% longer than the shortest path. So the path starts here, it goes to here. The blue line is the least risk path, the pink line is the shortest path. So visually you can see that the path is already choosing different areas according to the algorithm. So we wanted to quantify, kind of like know when is the path less risky to get lost in. So I summed up here a couple of options that we could use to quantify the risk. Field testing is asking people to walk around and see when they get lost, which is modeling, but we didn't really have that much time at this point. So we searched the literature and searched for parameters in wayfinding literature that determine the risk of getting lost. When do people get lost? When have they noticed that they get lost? Which parameters influence the risk of getting lost? So we have a benchmark parameter set determined. So you see that here. It's based on wayfinding literature both in outdoor and indoor spaces. Outdoor, because there wasn't a lot about indoor wayfinding, always came down to the same parameters. So I think also that the outdoor wayfinding literature might be similar, have similar results here in indoor, but obviously we need to test that maybe or consider it later. So a couple of parameters: drive complexity, the number of turns. It's obvious. The more turns you have, the more easy people get disoriented. The more easily they get lost when you're walking around. Number of turns is similar. Also, people that are familiar with the building, they use a direction-based strategy. So when they're at a certain position, they know the destination, they always try to minimize the angle between the current position and where they need to go. And if there are a lot of curves and turns, then it gets more difficult, especially indoor, because you don't see the destination point often. So they can get easily lost. The width of the corridors is also quite obvious. The wider a corridor, the more people think or perceive it as more important compared to smaller corridors. And the redundancy, it's the number of decision nodes along your path, also quite obvious. The more nodes you have where you have to take a decision, the more options you have where you can get wrong. And then the number of visible decision points at each decision point. There was some research that found out that unfamiliar users, because obviously the algorithm would be most suited for unfamiliar users. So unfamiliar users apparently use local topological qualities, and one of that is if I see more decision points ahead, I feel safer and I will continue taking my route because I already can think ahead further ahead. So our least risk path algorithm should have, or the results of that should have more visible decision points at each node compared to a normal path. So we applied that to that example that I showed you before. The first three rows are just the general results that we get from our algorithm. So it confirms again what the algorithm does. This risk path algorithm gives a longer path in terms of length, but a lower risk value. But then here it gets actually interesting. If we look at our parameters, then all parameters actually confirm that the shortest path is in this case less riskier to get lost on. So we actually should consider the shortest path as this risk path, although the algorithm obviously calculates something else. So it confirmed that there is actually a need to adapt and change the original algorithm, maybe take into account some of these parameters to get a better result and to calculate actually these risk paths instead of paths that are not easy at all. So then I'm at the conclusions. So our broader goal maybe, is to develop more cognitive algorithms for indoor space. In this case, we use the least risk path algorithm as starting point. Obviously, it needs to be adjusted. As I said, we're also busy with the simplest path algorithm, and we might actually combine both in a more general cognitive algorithm in order to help people navigate into indoor space. We found the limited differences between the least risk path and the shortest path in terms of length and risk value. And when there are deviations, the density of the network is key, and also the locations of the staircases and escalators and elevators. So the main connections, because those are limited, obviously, limits where you can go up or down. And then we also saw that the least risk path algorithm not necessarily calculates less risky routes. We think that a reason might be that the risk value needs a different meaning indoor, different weight, because now, if you remember, the risk value is only based on the length of the edges that you don't use. But obviously the width of the corridor is also important, the number of points that you can see, the number of turns, so there are a lot more parameters and variables that get involved in what is risky or not. And then the indoor network, I didn't really say a lot about that, but I think that the indoor network structure also has a big influence on our results, because now we used this geometric network model, which transforms corridors into linear structures, and in front of every door there is a node. But when I'm walking through a corridor, I don't perceive every single door as a decision point. I just know that I have to go to the end of the hallway, then I just walk and I ignore everything else. So we might need to move to a more hierarchical structure and see how that improves the results of our calculations. So I summed up some of the adaptations that we propose. Also, there are indoor wayfinding strategies. We might look into how people actually, unfamiliar users actually normally find their way in buildings, and what is found already is that they go to the central area, then go to the floor level they have to go to. and then find their way on that floor level. So we might try to incorporate that in your algorithm itself. That was it for now. If you have any questions, please ask.